Math 252, Appendix 1, talking about the gamma function, and we're doing, this is video 3 of 3. Because we're not trying to cram this into the end of the previous video, we're going to do a few more examples than what I said at the end of that video. So number 1, evaluate, this is from the problem section at the back of the Appendix 1. Number 1, evaluate gamma of 5. Well, for a positive integer, gamma of k is k minus 1 factorial. So that's just 4 factorial, also known as 24. C, we want to evaluate gamma of negative 3 halves. Gamma of negative 3 halves, we can use our formula, gamma of 1 plus x is equal to x times gamma of x. That, along with what we know of gamma 1/2, is equal to square root of pi. Well, 1/2 is minus 1/2 plus 1. So we write gamma of 1/2 is gamma of minus 1/2 plus 1. And that is minus 1/2 times gamma of minus 1/2 on one hand, but on the other hand, we already said that gamma of 1/2 is square root of pi, so this is also equal to square root of pi. Pi, not 5, pi, square root of pi. So we multiply both sides by -2, and we get gamma of negative 1/2 equals -2 square root of pi. And we did that once, we can do it again. So gamma of negative 1/2 is gamma of negative 3 halves plus 1, which equals negative 3 halves times gamma of negative 1/2 by gamma of negative 3 halves on one hand, but on the other hand, it's gamma of negative 1/2, which you just figured out is -2 square root of pi. And so gamma of negative 3 halves is equal to 4/3 square root of pi. By the way, using this identity, that was all I needed to say was to, when I was speaking in the earlier video about extending our definition of gamma to non-negative integers, other negative numbers that are non-integer negative numbers other than negative integers. All we really needed to do was to use this formula right here, just like we did just now, to find gamma of negative 3 halves. We can write it in terms of gamma of negative 1/2, which we can write in terms of gamma of 1/2, and now that's a positive number, so it's defined by that integral. All right, that was number 1 from the appendix section. Now, 1A and C, D will be similar, B is similar. Let's do number 3. Number 3, from the problem section at the end of the appendix, they tell you to use 1, which is that same formula about gamma of x plus 1. And the fact that gamma of 5/3 equals 0.89, which is an approximation, but we're not going to use that anyway. I think they made a mistake constructing this problem. Either that or they threw in a red herring. Either way, one way or the other, we're going to do the integral from 0 to infinity of x to the 4th e to the minus x squared dx. And this integral does not, turns out it does not have a closed form in terms of the elementary functions that you learned about in Calc 1 and 2. But we will be able to write it in terms of the gamma function, no problem. So The gamma function, the definition of the gamma function is that gamma of x is equal to the integral from 0 to infinity of t to the 1 minus x times e to the minus t. That should be x minus 1, not 1 minus x. dt. And we want to make this integral look something like this one. And so we're going to do the substitution that turns that into minus t. That is, t equals x squared. So let t equals x squared, so that that exponent will then become this exponent. And then x is going to be square root of t. We'll take t to be positive. Well, t is automatically positive. And what I should say is x is positive because we're going the integral from 0 to infinity. So we don't have to worry about the plus or minus. X is going to be the positive square root of t because x is positive in this integral. And dt is going to be 2x dx. So dx is dt over 2x, and x is square root of t, so that's dt over 2t to the 1/2. And now we can plug everything in and write everything in terms of this t and hope that we can now recognize this in terms of the gamma function. So we have the integral as x goes to 0, t will also go to 0. We gotta use this substitution to change these limits in general, but in this case, as t goes to 0, x goes to 0, and vice versa. As x goes to infinity, t will go to infinity. So we have the same limits for the integration. X to the 4th is t squared. And then we have e to the minus t, and dt, dx is dt over 2t to the 1/2. So now we can write this as 1/2 the integral from 0 to infinity of t to the 3/2 e to the minus t dt. And we can recognize that if we let x be 5/2. So this is 1/2 the integral from 0 to infinity t to the 5/2 minus 1 e to the minus t dt, also known as 1/2 times gamma of 5/2. Well, we can write that 5/2 as 1 plus 3/2. And so gamma of 1 plus 3/2 is 1/2. Now that's 3/2 gamma of 3/2. And similarly, that gamma of 3/2 we can write as gamma of 1 plus 1/2. So that's 1/2 times 3/2 times another 1/2 gamma of 1/2. Or, since we know gamma of 1/2 is root pi, we can just write this whole thing as 3 over 8 times the square root of pi. And you can recognize this is maybe the type of integral that we maybe have already seen and might be likely to see again in the course of the problems we're doing. And so that's some explanation of why we're working with the gamma function right now. But that's enough. So that's it, the gamma function.